Hello everyone. Today we're covering something that's quietly but significantly changing the way we interact with technology, the automatic speech recognition or ASR. This innovation in the field of artificial intelligence has widespread applications, making our life much easier in ways we might not even notice. I'm Joe, and welcome to my channel, Joe Explains Tech, where we simplify complex tech topics for everyone. Let's get started. Have you ever been stuck in the following situations? You are very excited about traveling and you're flying to a different country, but after you landed, you realize it's very difficult for you to communicate with local people because of the language barrier. Or picture yourself in a work meeting. Your duty is to writing down all the notes while trying to actively listen. It's overwhelming, and maybe you hope to have a magic software to help you translating all the speech to text. That's gonna save a lot of time and mental power. Or perhaps you are a content creator with a fantastic script, but recording and editing your audio spend hours and hours. It feels like a never-ending battle. The above scenarios are real-life issues that many of us faced a lot. So, if computer can understand human speech and translate their speech to other languages or to text in different languages, that will make our life much easier. Luckily, there are already quite some tools available to help people, like Google Translate, like DeepL also for translating, or if someone have questions regarding the language, they can ask ChatGPT. And there are also some AI tool like Whisper provided by OpenAI. You can use it for translate your speech to text. Or vice versa, you can use Resemble AI to translate a script to spoken language. And recently, Meta AI has also provided a new tool called Seamless M4T, which is a universal language translator. The idea of this tool is an all-in-one language solution designed to understand and translate both spoken and written words across over 100 languages. That's very impressive, right? The technology behind this amazing tool is the topic that we're talking about today, the automatic speech recognition system. So, how does ASR technology works? Before we started, let's briefly talk about what speech or what voice actually is. What you just heard is voice. Voice is created when an object vibrates at a certain speed, sending waves through the air that we can hear with our ears. Computers don't have ears, but they can use a microphone to capture the voice. Inside of the microphone, there is a component that vibrates when it picks up those sound waves, creating changes in electrical voltage. These changes of voltage produce an analog signal that can represent the voice. After that, the microphone has to transfer all the data to computer. The problem is, computer doesn't recognize analog signal. Computer only understands digital signal. So the microphone have to transfer the analog signal on the left side to digital signal on the right side. And this converting process is called sampling. Now, this green color waveform is digitalized voice signal. And the idea of ASR system is analyze the features of this digital waveform, then mapping the digital signal to human speech based on these features. Well, here I mentioned the word feature twice, and you may be wondering, what exactly are features means here, and why computer can recognize human speech based on these features? Let's explain the first question. What exactly are features of a voice with a simple piano example? Here I have a piano and I will play 7 notes for you. Please pay attention to the right side of the screen where I will display the analog waveform of these 7 notes. Did you notice it? When the pitch goes higher, the voice wave on the right side is oscillating faster and faster. Let's see it again. Now it's clear. Different voices have different waveform and different oscillating speed. This oscillating speed is the feature of a voice. When the pitch gets higher, the wave oscillates faster, and the oscillating speed is what we call frequency. And frequency is the key feature that speech recognition systems use to understand human speech. In the field of engineering, we use an algorithm known as fast Fourier transform, or FFT, to calculate the frequency of a voice. For example, the frequency of the note on the left side is somewhere around 420 Hz, where Hz is the unit of a frequency. Now, let's apply FFT to all the piano notes you just heard and calculate their frequency. You will notice that for this simple piano note, the frequency spectrum on the right side shows only one frequency component. Simple voice only have one frequency. What about a more complex sound like a chord? If I play a chord made of 3 notes, you will see the waveform get more complex and the frequency spectrum now have 3 peaks, which means this sound can be represented by 3 frequencies. Let's try one more like C major. Okay, C major also have 3 components. Let's make the sound even more complex. This time we try the chords with 4 notes. From the waveform, the sound indeed gets more complex, but even though the frequency spectrum is still quite simple, the complex sound can be represented by 4 notes. If we play one more chord, the result is the same. Okay, now we're clear about 2 things. First, voice is generated when an object vibrates at a certain speed and sending waves through the air. Second, frequency is how fast this wave oscillates, and frequency is the key feature of a voice. Voice can be represented by frequencies, no matter your simple voice like a note or complex voice like a chord. Let's explore a real-world example to see how speech recognition operates. When a man speaks the word hello, the microphone records his voice and transmits the data to computer. The computer processes the data, and this digital waveform is how computers see the speech hello. The sound of the word hello lasts approximately for 1 second. Engineers usually don't process signals of this length all at once, as it can lead to information overload and increase the chance of errors. The common first step is to divide the sound into smaller segments, known as frames. In our example, let's split the 1 second signal into 10 frames. Each lasts for 0.1 second, so 100 milliseconds. Next, we apply the fast Fourier transform FFT algorithm to each of these frames to transform the time domain signal into its frequency components. As you can see, FFT is helping us to see which frequencies are present in each small frame of the sound. You will also notice that each frame has limited frequency information with only a few peaks, which is actually beneficial for processing. However, even after FFT, each frequency spectrum will still contain a lot of data. So how can we condense this information while retaining the key features? Researchers and mathematicians have already solved this for me. They created a method called male frequency capture coefficients, the MFCC feature extraction. So in this process, it involves several steps like male filter bank processing, discrete cosine transform, and calculate delta coefficients. But don't be scared, we don't need to get too deep into the math. The only thing we need to know is the goal of MFCC is to represent each frequency spectrum with a 39-dimensional vectors. That's essentially 39 numbers that capture the most important characteristics of the spectrum. So in our example, where we have 10 frames, we would end up with 10 separate 39-dimensional vectors. After the MFCC feature extraction, the next step is to make sense of this data. That is where the acoustic modeling comes into play. In a typical ASR system, the acoustic model is trained on a large dataset that includes various accents, dialects, and tones of spoken language. After training, the model learns how to map the 39-dimensional vectors to a specific tiny sound with probability. The official name of this tiny sound are called phonemes, and they are important because changing one phoneme of a word can turn the word into another completely different word. For example, we have the word cat here. Cat has 3 phonemes, K and T. If we change the first phoneme, the cat will become a hat. If we change it again, hat becomes a chat or becomes a bat. Now you know how important it is to find the right phonemes if you want to determine the correct word. Once trained, the acoustic model can take a new set of 39-dimensional vectors and predict which phoneme they most likely represent with possibilities. So the next piece of the puzzle is how to determine the correct word based on the phonemes. Here you might wonder, if we know the phonemes of a word already, why isn't that enough for us to find this word? And that's because phonemes are like letters in the alphabet. Just like you know every letter in a word doesn't mean you can spell this word correctly. Knowing the phonemes of a word doesn't mean you can form this word correctly either. You need a recipe to guide you how to map from phonemes into the right letters, and also how to list these letters in the right order to form words. Because the pronunciation of some spell may sound similar, so in the end you may end up with different answers. The recipe should also tell you which word is the correct word you're looking for. This recipe is what we call the pronunciation model. It takes phonemes with possibility as input and maps these phonemes into the correct word. It also calculates the possibility of different words, so to decide which one is the correct choice in this language. The pronunciation model is crucial for a computer to recognize human speech. However, sometimes in language like English, many vocabulary can sound similar but mean very different things, and it's difficult to identify them purely based on the pronunciation. For example, let's take a look about this example. I need some flour for baking. Now we put phonemes of this sentence into the pronunciation model, and some words can be detected quite easily, like I, need, some, for, and baking. However, the pronunciation model has a problem when trying to processing the word flour, and that is because the phonemes of the word flour is this for. After we input these phonemes into the pronunciation model, it's very likely that we have 2 outputs. We can get the flour, which is food. We may also have the word flower, which is the plant. These 2 words have the same phonemes, so it's not possible for the computer to recognize them based on the pronunciation model. Even human beings may not recognize these 2 words without knowing the context. Yes, context. That's how human brain works. If your context is Gordon Ramsay teach you how to make bread, of course you know which flour he's referring to. The ASR system works the same way. It has to know the context of the sentence. This process of learning the context is realized by the language model. The language model will take the words generated by the pronunciation model as input. Now the possibility of 50-50. Then it will also look at other words in this sentence. When the language model reads the word baking, he will think, okay, then the first flour seems to make more sense here. It will update the flour to 90% of possibility and lower down the second word. If the sentence is about garden, then the second flower may have more possibilities, and so on. The last model that comes into play is called decoder. The input of the decoder is basically all the information we have gathered so far, from the phonemes identified by the acoustic model to the word recognized by the pronunciation model and the language model. The output of the decoder will be the final text. The idea of the decoder is to combine all the possibilities and search over all the word sequence to find the most likely sentence structure, which is the meaningful sentence. Let's take a quick overview here. The journey starts with a microphone capturing the sound. The microphone will translate the sound into a digital waveform. To simplify the following processing, this waveform will break down into smaller pieces or frames. The next step is to extract the frequency information from this waveform using FFT, and the red figure here is the frequency information of one of the frames. Because it still contains a lot of data, to simplify it, scientists find a way called MFCC feature extraction. After processing with MFCC, the frequency information will be represented by 39-dimensional feature vectors. The MFCC process will simplify the calculation a lot. The next step is input the 39-dimensional feature vectors into an acoustic model. Acoustic model will analyze these digital frames and then identify the tiny sound, what we call phonemes, that make up speech. The acoustic model may have bias, and the feature vectors may also contain noise, so the generated phonemes are with probabilities. After that, the next step is to input all those phonemes into a pronunciation model. The pronunciation model takes over to string these phonemes into actual words based on the language rules. However, sometimes in a language, different words will have very similar pronunciations, and it's not possible to recognize them just based on the pronunciation. In this case, the language model will suggest how this word can be best form meaningful sentences. It will take a look about other words in this sentence, then to update the probability of the unrecognized words. Finally, a decoder takes all this information as input and assemble all those words into the final text that represents what was said, and that is automatic speech recognition. The process we explained here is a simplified version because we didn't dive into programming and mathematics. But the whole process is still quite comprehensive, and the commercial product on the market is following the same design strategy. Let's take the Seamless M4T as an example. From their website, the design structure is first take the audio input and input the processing result to a speech encoder. The speech encoder will extract the feature of audio information and translate them into a decision model. The decision model is basically a pronunciation model and the language model to determine the information behind the speech. After that, if the user wants to translate audio input to text output, the decision model will transfer the information to a text decoder that generates text in different language. If the user wants to translate one language to another language, the decision model will transfer the information to first a text-to-unit component, then transfer them to an audio waveform vocoder, so generate a different voice in different languages. Now, let's end this video with a fun fact. The history of automatic speech recognition is already 100 years old, and the first proof of concept is actually a toy. When someone called Rex, which is the name of this toy dog, the dog gonna pop out from his toy house, and that is where the magic began. Hello everyone, I'm Joe. Thank you very much for watching this video. If you have any comments or advice, please let me know. Your support and help is greatly appreciated. If you like this channel, please don't forget to subscribe, and I hope to see you soon.